Okay, so last week we held the introduction about several different type of the definitions for the angle and direction. And there are also some other definitions about the angle and also the way for us to measure the angle. So this will be covered in the lecture today. First of all, one of the very common methods for us to measure the direction is using the compass, especially the magnetic compass. This one is very common for you. You can use your cell phones if you are using Android or iPhones. You will find out the compass app, and with that, it can tell you the directions of the line of the sight. With that, usually the compass will tell you the bearing of one direction. So this is a little bit different for the for some physical compass. If we are using the compass not from the app, not the digital ones, then you need to know how to get the directions of the one line read from the compass. For example, for this figure, you will have the compass where the compass will be divided into 4 regions: the northeast region, southeast, southwest, and northwest. And you have needle in the compass to direct to the magnetic north. And if you have the line on the sight, say that you're standing at point A and you want to identify the direction from A to B, then you have to use the compass to let the north direction mark direct to the target B, and with that you will have your needle pointing to the north side, pointing to an angle. And with that, you can read the angle, the direction of A to B as north 60 degree east. So this is as the line of sight is actually on the right side of the needle. If it's on the left side, that will be the north something on the west. Similarly, if we have the angle, say that if we have an angle reading goes through this direction, and the direction goes through this one, then you probably will have the measurement about the direction as south, say 25 degree, and this is actually to the west of this of the needle, so south 25 degree west. So that's the way for you to read the angle from the direction from the compass. However, the compass cannot give you the true direction of any line that is defined on the Earth. The reason is like the magnetic north or the magnetic south is actually different from the actual north or south. There's a small declination between the magnetic north and the magnetic and the true north. So we define this this angle difference, the horizontal angle difference between the compass needle and the geographic north as the declination. And this declination is actually changing over the time, and it's different at the various locations on the Earth. So whenever you are using the compass to measure direction, you have to do the correction for those declinations. And of course, I'm going to show you how to do the correction. Here's the one map which was showing how the magnetic declination is changing over the across the whole world. So in this graph, you can see there will be some red lines and some blue lines along those, each line will represent one declination. For example, if we are talking about the South Hamilton area, so which would be some place around here, the declination will be around 12 to 16 degrees. So this is actually a very huge difference between to the true north. So if you measure the angle is around the angle you measure is around say that the direction say that it's a 60 degree, then probably you need to add an additional 12 or additional 16 degrees to the angle you measured in order for you to find out the true north or the true south. And the declination could be even larger at some specific locations on the Earth. They could be as high as 40 degrees when it's close to the South Pole. And so this is about the declination. And we know that the magnetic declination is changing over time. So we have some rate, the secular rate, which means which will represent the changes about declination over 300 days. We also have the annual rate, which means that declination at every year, and the daily rate, which is of course the declination is very small, but it's changing over the time, even at one day. And also for some specific area with some magnetic disturbance, then you will observe some irregular declinations to the compass, and in that sense, the measurement, the direction measurement through the magnetic will not be accurate. The irregular would not be the part we're going to consider. We will just try to consider the way to handle the variations with certain patterns from the secular, annual, or daily changes. This is very important for you to use the compass to measure the angle and directions. So here I'll give you one example to see how we can do the correction for the declination with the angle measurement from compass. Assuming that we have the compass and we measure the line of AD, and the magnetic azimuth is 54 degrees 30 minutes. This means that the angle is measured from the magnetic north. And this one is conducted in 1994, and the declination for the area was previously calibrated and found that the interpolation from the isogonic chart in 1990, that would be 17 degrees 30 minutes east. And we also know that the annual change is about 3 minutes westward. So the angle will change to the west side at every 3 minutes every year. So with this information, we want to find out the true azimuth of the line from A to D. So now let's go to see what we can do with that. So to solve this one, we know that we are provided with a set of the information. We know the azimuth of the line A to D, which is measured from the magnetic compass as 54 degrees 30 minutes. And this is conducted in the year of 1994. And we also know that in 1990, the declination is 17 degree 30 minutes to the east. And also we know that the variation is 3 minutes to the west side. And this is 3 minutes per year. And we want to find out the what's the true azimuth of the line A to D. So with this information, let's go to first. Let's go to draw the magnetic north and the magnetic south, and also try to identify the angle or the direction of the line A to D in that region. So we have the magnetic north. So this is the north direction, and we define this as the magnetic north. And this would be the south, and that's the east or west, and that's the east. And we have the line A to D. A to D, the from the magnetic north, the azimuth is 54 degrees 30 minutes. So from the magnetic north. Let me try to make it more realistic. So from A to D, the angle is 54 degree 30 minutes. So this is the azimuth that we measured. And now we also know that this is the magnetic north in 1994, which is the year we do the measurement. And now the next thing we have to consider is where's the true north in 1994, and with that we can then identify the azimuth for the line A to D in 1994. So so assuming that we know the true north and the true north of the Earth. So we have the north, south, west, and east. Those are the true directions. Say that in 1994, in 1990, the value is the magnetic north is about 17 degree 30 minutes to the east side of the true north. So which means that if it's in 1990, the true north would be 17 degree 30 minutes to the east side of the true north. So that would be something like this. So this is the north in 1990. And we know that the magnetic north is moving to the west side at every 3 minutes every year. So this also indicates that you can find out that the magnetic north is changing. So it's changing at every 3 minutes per year from 1990 to 1994. With that, in 1994, you will see the magnetic north is located at that one. So we want in this problem, we first want to find out the declination. The declination in 1994. So to do that, the declination I just said is D, delta D, will be the so let's first go to see the changes of the magnetic north from 1990 to 1994. So assume that it's delta D. So it's changing at every 3 minutes per year. And from 1990 to 1994, that will be 4 years. So it's changing about 12 minutes to the west side. And then with that, we can find out the declination in 1994 as the declination of 1990. So this angle is what we measured as 12 minutes minus the value we calculated. So that is 17 degrees 30 minutes minus 12 minutes. So with that, we have the declination at 1994 as 17 degree 18 minutes. So this is what we get. And once we have the declination in 1994, we can easily identify the azimuth. So with that, what do you think the true azimuth of the line AD will be? So if we are provided with this one, with this declination, as what we get is 17 degree 18 minutes. What's the true azimuth of the line A to D? From this graph, what's the value you can find? Can you see the value? Okay, I can quickly give you the calculation if you need some time, if you don't get the answer. So there's actually another example for you to check how to calculate the how to do the calibration with the declination. So with that, the angle, the true azimuth will just be the original azimuth. For this specific situation, we want the true azimuth. The true azimuth will be the azimuth from the true north. So which means that you need to use the azimuth of the measured azimuth plus the declination. So that's the 1994. So we have the true azimuth, the measured azimuth as 54 degree 30 minutes plus 17 degree 18 minutes. So this will give you the answer as 71 degree 48 minutes. So with that, you can find out the true azimuth based on the declination that you observed in the previous years, and also the variation rate that you collect calibrated by the government or some other surveying organizations. So this is the first example about the corrections of the declination. Let's go to check another one. So in the second example, I provide with you about a bearing, a magnetic bearing as the north 34 degree 30 minutes to the west. And then this one is actually recorded in the old surveying plan in August 1910. And it's a desire to re-establish the direction of the line in 1995. And we know that in 1990, the isogonic chart shows that the declinations is 20 degree to the west of the area. And the annual change rate is 2 minutes to the east side. And then we want to identify the magnetic bearing which will be used to relocate the directions of the line in the field. We want to find out the magnetic bearing. So to do that, we want to find out first. We want to find out the true bearing of the line, or the true direction any kind of measurement, you can use the you can also use the azimuth. And then you need to convert this one to the magnetic bearing. Magnetic bearing in 1995. So by this would be the two steps for us to solve this problem. So first of all, let's go to draw the line. For this problem, we will start from a different approach. Let's first assuming that we know the true directions. It's not straight. We know the true north direction. So we know the north, south, east, and west. And then we can identify the north direction in the magnetic north direction in 1990, because we are provided with the information. In 1990, the declination is 20 degrees to the west. So with that, do you think where we should put the north direction, the magnetic north direction in 1990? It's here or in this, on the left side or on the right side? Is anyone able to provide the information?
The left side.
Yes, the left side will be right. And we know that will be the west of the true north. So the we know the value is 20 degrees to the west. So just draw the magnetic north. So this is the magnetic north in 1990, and the angle here is 20 degrees. So it's 20 to the west. And now we need to find out the estimated north, magnetic north in 1910 and 1995. So first for 1910, I'm asking the same questions. In which side should we place the magnetic north? On the left side of the north in 1990 or on the right side? Which one do you think?
Left side.
It is, yeah, it's still left side. So this one is actually determined by the variation. So we say that the annual change, the variation is 2 minutes eastward. So this means that the magnetic north is moving from west to east. So this is the direction for the magnetic north changing over the year. So apparently in 1910, there will be some just draw roughly. There will be some direction north. This will be 1910, and what with that for 1995? That will be obvious. It will be on the right side. So in 1910, that will be north. 1995, yes, 1995. And we can then identify these two angles based on the variation rate. So it's say that it's a delta D1, this is delta D2. So for delta D1, it's estimated based on the number of the years and the variation rate. So the variation rate is 2 minutes times the number of the years, that is 1990 minus the one previously estimated is 1910. So we have the result as so this is 80 is 160 minutes, and this will be the 2 degree 40 minutes. So that's delta D1, and for delta D2, it's between 1990 and 1995. So it's 2 minutes times 1995 minus 1990. So that is just 10 minutes. 10 minutes. So for now, we will then need to identify the declination in 1910. In 1910, what's the value of this declination? Do you have any ideas to find out this declination? What's the value do you think it is? Can you find out the value quickly from the assumptions?
20 degrees plus 2 degrees, 40 minutes.
It's one. Sorry, it's 1 degree. Can you repeat your answer? Okay, I probably can check the
20 degrees, 2 degrees, 4 minutes.
Yes, that's right. That's the right answer. Thank you very much. So it is the so we know that this angle is a 20 degree, and this one is a 2 degree and 40 minutes. So that is a 20 degree plus 2 degree 40 minutes. So it's 22 degree 40 minutes. And also we have to remember that this is the one to the left, to the east, to the west side. Sorry, to the west of the true north direction. And that's the first step for us to find out the declination in 1910. And then we need to find out the declination in 1995. So again, what's the value can you find? What's the value can you calculate for this declination? So I think I can quickly give you the result. It's so we know this one is 20 degree and this one is 10 minutes. So what we get is 19 degree 50 minutes. Right, that's the right answer. It's 19 degree minus 10 minutes, so we have the result as 19 degree 50 minutes. So you have to pay attention about the conversions between the degree and minutes and seconds. So with that, we will have the declination in the year of 1910 and 1995. And then we can find out the true bearing. The true bearing of the line, say that the which is line O to A. So we say that we know we have the line O to A, and the based on the assumption the line O to A as north 34 degree 30 minutes west. So in this graph, there will be some place here, northwest region. So the angle from the 1991 magnetic north, northwest region, so that is a 34 degree 30 minutes. And now we can find out the true bearing of the line O to A. Say that is A prime OA. So the true bearing will be the bearing of the line O to A plus the declination in this case. So we have the 34 degrees 30 minutes plus the bearing. So that is 24 degree 40 minutes. With that, we have the true bearing as 57 degree 10 minutes. And it actually falls in the northwest region, so we still have the bearing as north, so 57 degree 10 minutes to the west. And now the problem this is the true bearing. The problem then want us to find out the bearing in 1995. So with that, we want to find out the bearing from the north. So this would be the this is the north in 1995. So we will try to identify the bearing based on this magnetic north, which means that we need to find out the angle here. And with that, you can easily find out the angle, the bearing of the line O to A as the true bearing minus the declination in 1995. So that would be 19 degree, 50 minutes. So with that, you can find out the answer as 37 degree 20 minutes. So this would be the final answer for the bearing of the direction O to A in 1995. So these two examples give you some sense about how you can calculate the bearing and also the directions based on the corrections from the declination. Okay, so that I guess there will be some issue about this one. Let me just quickly correct it. There will be something. So the after that we will have some introduction about the how to use the angle to do the measurement, and so in your experiment, actually in a lot of the field experiments, we may observe
Geez. You just left.
Okay, I'm sorry. I think I just accidentally dropped the meeting. So can you see my slides now? Are you able to see the slides now? Okay, sounds good. And sorry about this kind of internet issue. So it's still recording. That's good. Okay. And so, well, I guess you missed this part about the measurement with repetition. So we are able to well, as I just claimed that in the field experiment, there will be a lot of errors. That could be some systematic errors, could be some mistakes from the operators. So we want to repeat the measurement a lot to make sure that the error could be minimized. And the repetition is the method of the repetition is the one that could reduce this kind of error. So here I will just show you the procedure of the repetition. So assuming that we are trying to measure an angle of two directions from O to A and O to B, and say that the angle is alpha, what we do is like we will first set an instrument set the instrument at the point O, and then we will point to A. And you can initialize this one to 0 or not, depending on your preferences. And then you will start the recording and rotate it to B. You have the measurement, you have the direct reading from the you have direct reading from the instrument. That will be the angle, the first measurement about the angle of alpha. And then we will, the next step, we're gonna lock the instrument and reverse the telescope. And then we will point to A, and then point to B and point to A, and unlock the instrument and start the measurement again, and then point to B, and then get the reverse reading. So this is the reverse reading, and we're gonna go back to step 4 and repeat this one for many times and get a lot of reverse reading, and eventually you will have a number of the repetitions. So you can repeat this one for n times. And with that, you will have the direct reading and the n times reverse reading. And we're going to use this direct reading and reverse reading to calculate the angles of the between OA and OB, which will be the alpha. There will be more details will be covered in the next lecture. I won't. It will take some time for me to explain more details, and I want to save some time for the first quiz, for the second quiz. So for now, I will activate the quiz on Avenue to Learn. So just a moment. And okay, so it's now available for you to work with. So you will have 10 minutes to work on the quiz. It's a very simple question, so you can quickly solve those questions. And after that, we will try to collect your answer, and I will explain the solutions in the next lecture. So you can start work on the quiz one. Feel free to let me know if there's any difficulty for you to access to the quiz. For this quiz, it's still based on your attendance. I hope I can use the quiz to understand your understanding about the contents covered in the class. With that, I can try to do some adjustment about the homework assignment and also the exams in the future. So you can work on that now, and once you have 10 minutes to work on that. Once it's finished, well, we'll probably close the lecture today. So with that, I will stop recording the video.